The punchline is the outline is that we will first discuss that long strings in AdS can be thought of as a conformal defect in the boundary theory, and then we will talk about nonlinearized conformal symmetry or nonlinearized AdS isometries and do some calculations at weak gauge coupling in QCD. Then we will do calculation of strong coupling, strong Yang-Mills coupling, meaning that a small effective string coupling, and then we will discuss can we actually compare or match these two calculations that we get strong coupling. So first, very quickly, let me do a lighting review of flux tube, what we know about flux tubes in flat space. So that's of course something that Sergey and I and others work for a very long time, and most of you heard many talks from us about it. So again, setup as we focus on pure Yang-Mills, let's do large N. Some of the things I will say will be true at finite N and with matter, but okay, let's have the simplest setup. So we have pure large N Yang-Mills. I will discuss 4 and 3 dimensions. In both cases, of course, it confines. And then in particular, very flat space, it can be compactly defined on the circle and then simulated on the lattice. And then the setup here, okay, so this is a cylinder, right, of some radius r. I take r a priori much longer than the QCD scale, and then I insert some sort of wiggly string that creates an excited state of my flux tube. And then I can study its spectrum. And then so many people have done it. The most recent updates are in this paper by Gabriel, Sergey, and oh no, so Gabriel is not on this paper anyway. Sergey in France. Okay. Well, Gabriel also worked on it for doing rotating strings. Anyway, so if we look at this data, very brief summary is that these energy levels, they look quite regular. There is a single massive mode that lives on the world sheet of the string. So these are 4-dimensional strings. And this is the world sheet axion, right? It's a parity odd state. And then basically the idea is that these interactions, leading interactions of the Brennans that describe the spectrum of these excited states, it looks like some sort of consistent with what we can call this TT bar deformed spectrum for those familiar with this TT bar story, but otherwise it's some sort of square root formula. Of course, if you read any textbook on string theory ever in your life, you recognize a formula like this shows up with some light quantization or whatever your favorite way of quantizing string is. But here it's not very okay. There's some explanation why some formula like this should work, but for now let's just treat it as some sort of phenomenological fitting formula that works well. Okay, so that is my one slide summary of the results in flat space strings. So now in 3 dimensions, this story is even simpler. There is more precise lattice data. There are no massive particles on the world sheet, and then okay, there's some leading corrections to this square root type formula. They have been measured. Okay, so the punchline is that we understand confining strings as an effective theory in the limit when the length of the string is longer than the QCD scale, and it doesn't look terribly complicated, okay, as an effective theory. So it's not, we don't have some proliferation of new resonances that are unexpected, okay. And the question is, okay, can we connect this effective field theory to gauge theory degrees of freedom at energies that are larger than lambda QCD, right? Because at energies above lambda QCD, we expect to be able to describe this system by a perturbative QCD, right? This in terms of gauge degrees of freedom. And to me, this is more or less the whole point of understanding confinement, right? That we want to understand how the gauge degrees of freedom are connected to the stringy degrees of freedom, right, of the confining string. Very good. So in flat, so we can say, okay, why don't we just take this circle and make it very small, right? So then we'll go to high energies and then try to do things perturbatively. But of course, it's not that simple, right? Because if we do it in the most naive way, the theory deconfines, and we're going to lose computation. We lose our object that we studied, right? Which is this confining string that was winding the circle. Of course, there are some modification of this procedure, possible ways to get around, but I'm just saying the most naive thing fails, right? For an obvious reason. And here comes under the Sitter space. So now instead of putting our QCD on a circle, we're now proposing putting it in a rigid AdS background, okay? And then let me pick Neumann boundary conditions.
Of course, there is a way to avoid that.
Medad, I mentioned it. Thank you. Yes. But okay, the punchline is that that now we propose to do something different, and then we put things. Yeah. By the way, sorry, I'm not almost have no references on my slides apart from some papers. Okay. Sorry about that. When we write a paper, eventually we'll put hopefully all the references in. So now we will put Yang-Mills on rigid background, and now I want to emphasize that this is not some holographic QCD. Okay, I'm just taking QCD and putting it on rigid anti-de Sitter space. Okay, there is no holography here. And now what we get is that now there is a dimensionless coupling, right, which is the lambda QCD times the AdS radius. And then if we take this dimensionless coupling large, we're back in flat space. And then if we take this dimensionless coupling small, then basically running of Yang-Mills stops at AdS radius, so we get a weakly coupled. Okay, and then likely there is no phase transition as a function of R AdS here. And then for any coupling, we get an equivalent description of our system in terms of non-local boundary conformal field theory, in which in some sense the gauge field survives because we have this Neumann boundary condition. That is more or less the picture that we have our Yang-Mills sitting inside of, let's say, Euclidean AdS, and then it gives us a one-dimensionless conformal field theory. Okay, so the story of studying QCD in AdS is not entirely new, and especially recently there was some revival of these ideas. But okay, now the next ingredient is that on top of just having QCD in AdS, we're adding our favorite long confining string. Okay, so the boundary description corresponds to putting a Wilson line, that is, so this is a time slice, so Wilson line is represented by a point, and then it creates this long confining string that stretches radially from one boundary of global AdS to the other, and that is kind of a 3D picture that I try to visualize here. So you have this world sheet that is AdS2 inside of AdS-D, right? And now an important point that in AdS confinement occurs even at weak coupling, okay? So gauge field is confined by AdS curvature in this case. So to see this, it's convenient to write AdS4 metric as a summary of AdS2 factor times the transverse coordinates, and then there is this exponential potential well that basically forces, even at weak coupling, even at zero coupling in a sense, all the flux lines to still lie on this two-dimensional surface. And then basically you can then KK reduce on this AdS2, and then what you get at leading order, some 2D Yang-Mills on AdS2, and then plus some KK modes, okay, some adjoint matter coupled to this 2D Yang-Mills. So that is the picture. And then you have some string tension that now when we change AdS radius, first string tension is just explained by the AdS potential, and then it saturates and stays constant and asymptotes to the flat space string tension. Okay, so that is the setup. Are there any questions about the?
This AdS basically means that it's finite, right? There is no.
Well, AdS, as also Liam emphasized in his talk a couple days ago, AdS in some sense is finite and in some sense is infinite. That is a little bit of a difference with the setup that Medad is referring to, where say you put it on a torus and kind of torus is finite. So in AdS, really what we gain here, let me just answer to this your question, right? So it's finite in the sense that RG coupling runs, but it's infinite in the sense that we have asymptotic observables, on-shell observables, okay?
But it is clear to them redundant because say you have a large time, for example, right?
Infinite, yeah.
Some kind of non-compact direction.
Yeah.
And then we think it's an Euclidean AdS, it does not exist.
No, there is still a kind of a non-compact. So if you have a massive excitation, it takes an infinite time to reach the boundary. Yeah. Whatever. I mean, whatever time means in Euclidean, right? But the string is infinitely long in this sense. Okay, very good. So now from the boundary point of view, the string is a conformal defect that breaks. So and another kind of feature of AdS, right, is that I'm not breaking any isometries of flat space when I'm putting my string in AdS instead of deform them. But AdS has, of course, as many symmetries as the flat space. Very good. And then the string, it breaks the symmetry down to the 1z conformal group times rotations around the string. Okay, and now crucially, over this defect, we have perturbative control, both at weak and strong coupling. And we can compute the same observables. And the reason is that we have the Goldstone boson that lives on the world sheet of the string, or in this defect language, it's a displacement operator, which has protection dimension, okay? So it has dimension 2. At weak coupling, it's identified with insertion of field strengths into my Wilson line, okay? So there is a state operator correspondence that all the states that I have on my world sheet can be described by inserting operators into my boundary Wilson line. And in particular, there's a special operators that are protected. They have dimension 2, both at weak and strong coupling, and do not change. Now, other operators I can insert, their dimensions are not protected, and that is basically the interesting data that describes fully the theory, okay? Very good. So now in 4 dimensions, there is one operator that, again, we think are in some sense special. It starts again as dimension 2. It is this Fij operator that has the quantum numbers of the axion. And then what we believe is that is indicated by these red lines. When we go to strong coupling, this energy level should acquire linear growth consistent with having a massive particle on the world sheet. Okay. Very good. Because if we have a massive particle on the world sheet in flat space, we should also add it in our world sheet once we put the thing in AdS, okay? Definitely this at large radius. Very good. Okay, I should be moving a little bit faster. So our concrete goal is now to match this weak and strong coupling expansion. Okay, and now I switch to the discussion in 3 dimensions, okay, which is similar, but it's a bit simpler. So I only have one displacement operator, no massive particles on the world sheet, and the symmetry coset is like this, okay? And basically, philosophy here is that I'm going to make expansion around weak coupling. That's some sort of analog of 4 minus epsilon expansion in Wilson-Fisher Fricks point, right? So I want to go to some order 1 coupling, and it's not guaranteed to work, but okay, we know that sometimes this works. So let's see how well we expect it to work. So at weak coupling, we have a very powerful way of doing the calculations is by using these nonlinear symmetries, to which I alluded before. So that is something that was worked out by Barak and collaborators. So you can ask him for technical details. I'll give a very intuitive explanation for what these nonlinear symmetries are. These are just direct analogs of soft Pi theorems in anti-de space. So basically what you do, you have some, so remember, everything is in 1 dimension now, okay? I'm doing boundary 1-dimensional calculation. So tau is the time goes along my defect. So I insert, say, 3 operators, and then 3 generic operators, and I split displacement operator. So now, if I integrate this with tau to some power L being 0, 1, 2, 3, that corresponds to 3 conformal transformations. So this correlation function should not change, right? So that's the usual logic behind soft Pi theorems. Like I have the, I act with my transformation, and that's a word in it, right? I mean, the correlation function basically doesn't change. Now, you do some machinery, you use linear linearized conformal symmetry, use crossing, etc. You define this kind of integrated constraints, right? So you should think of this. So these are some constraints on 4-point functions of, in this case, displacement, operator, okay? Some particular case, I made a choice for my 3 operators. I get this type of integrated constraints. So this is really the analog of a soft Pi theorem. Now, then there is another constraint, which is basically a double soft Pi theorem, where you insert 2 soft Pi's, and then you get some non-trivial right-hand side, which is some sort of linear transformation that appears from the commutation relation of the conformal. Okay. So these 3 things, again, these are direct analogs of some current algebra results, you know, the Weinberg in the 70s, whenever he did that. Good. Now, these are true in general, but how can we make them useful? To make them useful, let's apply them to perturbative expansion with coupling. And something interesting happens, that even when we do free theory calculation, there is, because of large N, this cross diagram is absent, right? You can only have this and this contraction. And then we have some corrections when we start changing operators. Now, there's something puzzling. When we apply our nonlinear constraint to this first line, which is 0 order in the coupling constant, we do not get zero. So now, how could that happen? Okay, because all these things are suppressed by power of a coupling constant. So the only way it can happen is that these guys develop some singularity. Again, it's a direct analog of sort of singular terms that appear in the soft pi theories. So this singularity can only appear if you have an operator of some particular dimension, okay, that is close to integer. So it turns out if we take the whatever operator of dimension, so it turns basically if we insert operator of dimension delta O, then we need an operator with dimension delta O plus 1 plus something small, where small goes like 1 over g annual squared. Okay, now let's apply it to the simplest case where operator O is itself a displacement. Then you go through some calculation, you immediately conclude that you must have an operator with dimension close to 3, which I call here d. So it's a transverse derivative of displacement. And immediately, because this thing evaluates to some -5/3, and this interacting contribution evaluates to the square of OP coefficients divided by anomalous dimension. So you immediately get a relation between the anomalous dimension of this unprotected operator and its OP coefficient. Okay, so that is the simplest setup. Now you can do other external operators. Turns out you have infinitely many constraints. You don't need to absorb this formula. You get infinitely many constraints of this form. Turns out that this you can plug it into the you can solve this recursion relation and fix an infinite set of OP coefficients and anomalous dimensions, okay, to leading order in G without doing any actual perturbative calculation, just from current algebra. Okay, very good. So now you may say, okay, maybe that's something complicated. Maybe we missed some terms, some singular terms in this constraint. So then we can also go and test it by direct bulk calculation. So then you just go compute a Witten diagram in Engel's theory. And kind of the way to do it is by using this KK reduction that I mentioned. So with KK reduce our gauge field to AdS2, we get effectively some 2D Engel's theory. With some method, we do a Witten diagram in this 2D Engel's theory and get an answer. Actually, we calculate a more general OP coefficient, but once we set the external dimensions of the operators that we were able to calculate with the help of nonlinear constraints, this formula reduces to the formulas that we had before. Okay, so that is a nice cross-check by direct perturbative calculation that our nonlinear constraints, we're producing something. Okay, very good. So let me then move to strong coupling expansion. So now I'm going to the right part of my plot of dimensions. I'm going to very large radius, and I'm using effective string theory description. And as I emphasized, there's some observables I can match because displacement operator I can identify with a Gaussian plot. So here, okay, here nonlinear constraints are not, I mean, they're still useful, but they do not allow me to do calculation that quickly. Here you actually need to compute some Witten diagrams, and then you have this effective action, very similar to flat space calculations. Then you can also calculate anomalous dimensions. So instead of going into details of these calculations, let me take, some broader view. How close are these theories at weak coupling and strong coupling? And to do this, let's do first just a counting of operators. How many operators do we have on the left and on the right? Because that we can do exactly at weak and strong coupling. So at weak coupling, which is a very similar exact formula, that number of operators goes just of primaries of dimension delta go like 2 to the delta minus 3. Okay. At strong coupling, there is a slightly more complicated formula, but asymptotics here is Carnegie, of course, which is e to the square root of delta. So how can this work? The only way that this can work is that at strong coupling, basically when you take an operator and you track it from weak coupling to strong coupling, then its dimension should basically square, okay, up to some order 1 coefficient. That's the only way to match these asymptotic formulas. And in fact, I invite you to better think about this formula in the opposite limit, so that the dimension at weak coupling is the square root of it at strong coupling. It's at least for large enough dimensions where the asymptotic formulas start to work. Okay, so dimension at weak coupling is the square root of dimension of strong coupling. Sorry, didn't say it correctly. Now let's do some more careful counting. So what you see in this this table on this plot, they represent the same information. They basically, you take here, I mean, you do resolution by various discrete symmetries that we have on the on the worldsheet, and then you can basically match. You take some operator, it has some delta strong. Here you go from 0 to 20, and you see, okay, where can it go at weak coupling? And what you observe from this table is basically not so many checks. For example, 12 can only go to 6 or 7, okay? And then you can, okay, this plot makes it up to somewhere up to 50. And the punchline that basically, first of all, the formula, when you take an operator of delta weak, the function of delta strong, it almost doesn't depend on the other quantum numbers of operator, and it's very well matched by the square root formula. So this is just another visualization of the same data, right? Here I start, okay, fewer operators, but here I start at weak coupling, and actually when you see solid lines, is already computed to 3-level anomalous dimension, and then this dashed lines is not like some Padeo or whatever, it's just by hand interpolation. But you see that these lines do not seem to do anything too crazy. However, as you know, say 6 goes to something like 10 or 11. So you may say, well, that's quite a large anomalous dimension. So how can I be, optimistic that I can compute this perturbatively? However, most of this change in anomalous dimension is accounted by the square root formula. Now, remember, in the beginning of the talk, I reminded you that the square root formula should look for you familiar. Let's recap the cylinder formula, where I said that the spectrum of dimensions also is kind of well matched by something like square root. The only problem that in this square root, we couldn't take r to 0 because we had deconfinement. While here I have, if I define my lambda is r, I introduce r AdS times ls. Let's consider sort of a fitting formula for this, which I just copy paste from here and replace r with r AdS. And so this formula satisfies the condition that when I take my lambda to infinity, that just becomes delta strong. And when I take lambda much smaller than delta, it becomes square root of delta strong, which matches very well delta weak. So basically, this formula works pretty well for most of the dimensions we have here. But now I actually, I don't have to treat it as just as this fitting formula. I can also match it at weak gauge coupling or equivalently strong worldsheet coupling. Okay, so let's see, what can we do next? Okay, so first thing is that the square root formula, I'm pretty sure that it should have some very simple worldsheet origin, probably coming from some clever gauge. And I want to emphasize that the formula, it is completely universal. So it works for all confining and also critical or strings, in a sense, critical strings and AdS, which are holographic. So the only conditions here is some large N gauge theory UV completion. I think that even for Sergey and Gabriel p-adic strings, that formula should work. So it's really universal. Okay, so there should be some simple explanation, but it is not known. Like for flat strings, you can go to Lightcon gauge and derive some formula like this. But I think the formula should be derivable. So now after we understand this formula, we can push both weak and strong coupling expansion at higher loops. So just to tell you that an analogous problem in N=4 that was done at 3 loops on both sides. And there are many powerful tools that people working in particular N=4 developed, like dispersion relations, and then that also Liam referred to in his talk a couple days ago. And then we can use our nonlinear constraints. So these calculations, okay, I don't know, it's 3 loops, but in principle, 3 loops have been proven to be doable. So far, we did just 1 loop, right? And 3 levels. Okay, so now then, in the middle at intermediate coupling, you can do some bootstrap numerical, TFT1 bootstrap, to bridge the gap. And then basically after we account for the square root formula, I think I can, okay, I don't bet or whatever, my default expectation that this perturbative expansion will converge very well and will just match weak and strong coupling expansion. Now, then next exercise is repeat this in 4 dimensions. So now we have some new ingredients. We have the axion field, right, that maps to Fij at weak coupling, and then we have some additional constraints from approximate conformal symmetry. Now I'm not talking about the 3-dimensional conformal symmetry. I'm talking about 4-dimensional conformal symmetry, which is true in the UV in AdS. And then basically, for me, confinement here is explaining the inverse of the square root relation. It's how do you get delta strong as a delta weak squared. And I suspect that this is basically the effect of the A0 KK mode in this weakly coupled description, or in other words, just physics of 2D amines coupled to matter. So this may sound to you kind of like a grand proposal, with the difference that that is actually doable. Definitely the first 4 steps, and I don't think not even in 5 years, but in principle, hopefully much faster. Okay, so there are many other open questions that referring to what Midad alluded to. We have some weakly coupled compactification. So what happens to instanton monopoles? What is the relation to other compactifications that Alexei, Midad, other people worked on? What happens if we add supersymmetry? What happens to short strings? You can study them by studying on the rotating string that is again long and large angular momentum. All of this is doable. And then, okay, kind of going a bit more ambitious. So very similar problem was basically solved in N=4 superamines. And there you can see explicitly how gauge field modes geometrize to become composite Goldstone operators. So at weak coupling, you start with some derivative of your field strengths that we related to, okay, some KK mode in the bulk, and then this gauge field, okay, it's a colored object, and that geometrizes and becomes some basically Goldstone operator to some power. And I think that this phenomena, even though strongly coupled, is universal for things like N=4 superamines and QCD and pretty much any gauge theory. And I remind you that once placed in AdS, so long strings in both cases, they correspond to conformal defects. Okay, so kinematics becomes very similar for confining and for conformal theories. So the most ambitious goal here, of course, would be to take the flat space limit, flat or high energy limit at the level of this weakly coupled effective two-dimensional gauge theory description. Okay, I remember the zero coupling, we basically have an effective two-dimensional gauge theory that describes our string. And what you want to do, you want to take the flat space limit at the level of this description. That will basically provide a UV completion of the world-shape theory of the QCD string, which is kind of the ultimate goal in this part of research direction. Okay, so that's what I wanted to say today. Thank you for this talk.
I would try all this out in the case where more though, like vortex trace in the leading column. I mean, they have people with both description, and we also know the UV, the runners are good coupled, so you can test everything that you're doing in that context. Let's see how well you can do.
Yeah, I agree with that. Definitely an interesting, we can add it on this list. I agree, and I was thinking a little bit about it. One thing that you don't have there is large N. So this property that is, I think, crucial. So large N was important for it. So when I said that this thing is completely universal, I referred to this string theories or confining theories or whatever that have a large N limit. Because the origin of this formula, right, it is large N. It's because I counted operators at weak coupling, and I got a power law, not e to the delta is as opposed to e to the square root of delta. And that of course only can happen in large N theory, right? Because the origin of this formula is instead of counting partitions, I'm counting just number of words I can make out of given letters, right? But I otherwise, other than testing this feature, I agree. Yes, I agree.
So, shall I think about this? Let's start from flat space description of vector strings.
Yeah.
So, shall I think about this as a kind of indication that it's in some sense on the worldsheet it's less sure to add something like 2D mills? It doesn't have degrees of freedom, but
well, I'm trying to say this somewhere here, right, in this phrase,
right.
But it's not. You see, this 2D mills degrees of freedom, they become. So these are 2D mills degrees of freedom, if you like, okay, colored matrices, and they become Goldstones. So you may not you may be double counting if you mix the two. Of course, you can imagine some sort of description, some kind of Haber-Stratonovich sort of thing, right? Where you have kind of two fields, you integrate one of them, you land on this description, you integrate another, so you could imagine something like this, but I don't think you should be literally double counting.
It's not like you should be UV complete in the
Yeah.
in 2D.
Yeah. I'm trying to UV complete them in 2D. And Nielsen, kind of the conjecture here is that the effect of string tension, which takes a square root, right? So let's pretend it's a critical string, right? And we found some light cone gauge. Then effect of finite string tension. So that you have some interacting theory even in the light cone gauge. But then effect of string tension is taking square root of energies, right? Now you're asking yourself, okay, but on the Young-Mills side, what is taking a square of energies? And I'm saying that this is the formation of the string, which is just the 2D Young-Mills dynamics, but we haven't made it precise yet. But I'm saying that in n equals 4, exactly the same thing happens. It doesn't matter that you ended up in AdS 5. Who cares? You have just one more Goldstone boson. I mean, it's sort of a minor detail, but there you can actually see, very well. I like also to kind of conclude with this plot from Collegrom paper where these lines are plotted with precision of something like 10 to minus 60. Okay, and this plot it describes I want to say basically the same phenomena as this plot with some additional symmetries present in that problem in Epsilon here.
When you go to page 5, there was a plot there, right? With 5 months.
Sure. Yeah. That was the sorry, this or
This one.
yeah.
What are you plotting here?
Here I'm plotting the string lengths, whatever, string tension, inverse string tension as a function of, so I fix lambda QCD and I change AdS radius.
So this part of this plot is calculation and this part of the.
Here nothing is a calculation. No, this is well, if you want asymptotic limits are, this again, I'm not sure if it's a calculation, it's asymptotes to something that I define as flat space string tension.
The flat space string tension.
Yeah.
And the small RADS part isn't a calculation.
Yeah, that is the calculation. That is, if you like, very analogous to Aldaim-Aldacena calculation in the comments of large spin paper. So basically, I'm just saying that here I KK reduced to 2D Young-Mills, and then I have the string, and at leading order is given by just 2D Young-Mills string tension, whatever.
Essentially, the behavior of string tension, if you go from big coupling to from.
Yeah.
This is the behavior that I know, calculable with all theories which are calculable figures.
Yeah. I'm not again. I mean, as you've seen that it's one of the things on the list is to, understand this connection. I'm not. Yeah. I agree. That's an interesting part. Yeah. We want to understand. I'm arguing for some benefits of this AdS calculation, mostly because we managed to preserve many space-time symmetries. That's what allows us to kind of do many calculations in this case. But I agree. There is. It would be nice to understand in details how the physics match between these different compensifications.
Right. More questions? Thank you. Again.